Okay, thank you. And I just wanted to clarify something. So, since it's going to be a long talk, should we take a break midway? Uh,
Mm.
yeah, so maybe you can take a 5 minutes break midway. Okay, hello everyone. My name is Ankur. I'm a graduate student at Carnegie Mellon University and I work on multi-agent reinforcement learning. I am supervised by Katia Sycara. I am happy to be here today to talk about our paper, Natural Emergence of Heterogeneous Strategies in Artificially Intelligent Competitive Teams. The title seems a bit daunting, but sometimes we have to come up with such titles to get attention. So yeah, here's a quick link to our paper and the code repository. So here is the outline of today's talk. I have divided it into two parts. First, I'll go through preliminaries. I'll talk about what is machine learning, what is deep learning, and then we'll move on to some more interesting stuff, what is reinforcement learning, which is a technique that we use in our paper. And then I'll talk about what is multi-agent reinforcement learning. After we are done through the preliminaries, maybe we can take a short break. And then after the break, we can talk about the particular details of our paper, and we'll talk about what is the problem that we are trying to solve, what are the challenges, and we'll talk about interesting stuff like graph neural networks. And after we are done with our paper, I'll have a short conclusion where I'll talk about how you can get started with RL if you are interested. And I hope you find it interesting. So let's start with the preliminaries. So machine learning. So machine learning is the study of computer algorithms that allow computer programs to automatically improve through experience. So now this is extremely interesting. It says that it's a computer program that can automatically improve through experience. It's great because just think about it. In your entire life, if you have to learn just one thing, it could be machine learning. And if you have any new problem, all you need to do is tell your computer to use machine learning to solve it. So your whole life can be solved using just a simple thing that you need to learn. So there are a few categories within machine learning. We have supervised learning, unsupervised learning, and then there are things that lie between supervised and unsupervised. Among those things, we are just going to talk about reinforcement learning, which is what is relevant to our paper. So what is supervised learning? Supervised learning is basically learning from examples by imitating. So we are given a training data, which is a set of inputs. Let's call them X, and we are given the true labels, the Y's. And we can then train a machine learning model on this. And at test time, we are asked to predict the label of a new unseen input, a new X. And this is really how you would probably learn many things. And this field has seen a lot of progress, and today, as of today, supervised learning is being applied in many areas. And some of you are from machine learning background, so I believe you're familiar with supervised learning and know that it's already being used in the real world. So let's take a look at an example of supervised learning. Here we have, let's say we want our machine learning algorithm to classify cats versus dogs. So we are given an input image, which is X is our input image, and Y is whether it's a dog or a cat. So on the left hand side, we have some training examples. This is called the training data. So we have a data set which has some examples of cats and some examples of dogs. And we train our model on this. At test time, we are shown a new image, and the algorithm is supposed to tell us whether it's a cat or a dog. Now, just think about how you learn to distinguish a cat from a dog. When you were young, someone, maybe your parents, told you that this is a cat, this is how a cat looks like, and this is how a dog looks like, and that's how you learn. That's how you can classify a cat from a dog. So supervised learning it really makes sense that we learn from examples. When we are shown something, we learn from that example. Now, there's a problem with supervised learning. It needs a lot of training data. And what I mean to say is that we need some photographs of cats and some photographs of dogs. And not just that, each photograph should be labeled with its true class. Each photograph should say that whether it's a cat or a dog. And this requires human effort. You require a human to sit down, click pictures, and label all the images. And and we are trying to do machine learning. We want the machine to do stuff by itself. We don't want to put in human effort. So then let's talk a little bit about what is deep learning. So deep learning refers to using deep architectures containing many layers stacked together for machine learning. So really it's a part of machine learning, you can say. And when people talk about deep learning, they usually refer to neural networks. It's not necessary, but usually people mean neural networks. So what is a neural network? Neural network is a structure like this, in which we have nodes and we are given some input, which is fed into these nodes. And then these nodes do some computation and pass an output to the next layer. So we have one more layer over here. And then these nodes again pass on to the next layer. And here we have 3 layers, but we could actually have many layers, as many as you want. And these nodes really try to imitate the neurons in the human brain. So they try to like do some kind of computation that resembles what happens in the human brain. And this whole model has some parameters. Usually it has a lot of parameters, and let's call them together to be theta. This theta represents all the parameters that are inside this model. And after doing the computation, they give an output. So in this case, the model should give 2 outputs. It should say, what is the probability that this image is a cat? And what is the probability that this image is a dog? So we would like our model to give high probability for cat in this case and low for dog. And then let's talk about a popular algorithm, which is called gradient descent algorithm. And this is really the algorithm which is the most common algorithm that people use to train neural networks. There are, of course, advancements that are built upon this, but the basic idea is something very simple. So first you need to define an objective or a loss function. Let's call it j theta of xy. As you know, x is input, y is output. And when I write capital X and capital Y, in this, I'm trying to say that I'm considering a whole set of inputs, many small x's and many small y's, and theta is our parameter. So let's look at some examples of objective functions. First we have this objective function. This is called the cross entropy loss. Here yi. So here we have a summation. The summation is from I equal to 1 to n. So these are our training examples. Let's say n is equal to, say, 10,000. We have 10,000 images, and we are summing over all of them. And then there's a negative sign, and then yi is the true class, whether the ith example is a cat or a dog. And p theta of yi given x is really, given the xi, what is the probability that our model says that yi is what is the probability that our model assigns to yi? So we want to minimize this term, and this is our objective. And this is really a classification problem, because we are classifying a dog from a cat. And here we have another example. This is called the least square objective. So depending on your problem, first you really need to define what is your objective function. Once you define the objective function, the algorithm is extremely simple. It says that you have your current value of theta, subtract an alpha, which is called the learning rate, and multiply it with the gradient of your objective function with respect to your parameters. And you subtract it from your current theta, and then you do this iteratively. If you look at this diagram on the right hand side, it would probably make more sense. So here in this diagram, W is the same thing as theta. So W are our parameters, and this is our objective function. We want to come to this point, which is at the bottom. We want to reach there. That's what minimizes our objective or our loss function. So, so if you are on the right hand side, you would have a gradient that directs you to the left hand side. And if you are on the left hand side, you have a gradient that directs you to the right hand side. And after many steps, if you take multiple steps, you come to this local minimum. Yeah, and so we talked about supervised learning. Now let's look at the next category, which is unsupervised learning. So unsupervised learning says that we are only given the inputs and we are not given any labels, and we need to find some pattern in the data. So for example, here we are given some points, some data points. We want our model to find some pattern, And the model says that there are 3 clusters in these points, and which makes sense. There are 3 clusters among these points, but we didn't have to tell the model that these are the clusters and you try to imitate what I'm trying to say you. It had to figure out this pattern by itself. And finally, we are coming to reinforcement learning. And this is where things get interesting. In reinforcement learning, there is an agent that can act in an environment and it gets a reward at every time step. The agent's goal is to select a sequence of actions that maximizes the cumulative reward. And reinforcement learning often happens through trial and error. You try something, you fail, you try again, you fail, and finally you succeed. Now just think of how you learn to walk. So surely when you were young, when you were small, like 1 year old or something, you saw your parents, you saw other adults walking, you maybe tried to imitate them, but definitely you didn't get up and walk straight away. It was not supervised learning. You couldn't do it right by looking at their data set. You had to try it yourself. You had to take actions in the environment, and you had to do it through trial and error. On the left-hand side, we can see a baby that's trying to crawl. Its real objective is to walk, but it's trying random things, whatever works for it. And it's really not able to walk at this stage, but it tries for many days, many months, maybe for a long time it tries. And eventually it's on the right-hand side, we can see that the baby is able to walk, and it's even able to perform some dance moves, which I believe you are familiar with. So yeah, and if you think of RL, it's really interesting because many problems in the world, in real life, can be formulated as an RL problem, really. So really, this is a technique that can be applied to many areas, which is what makes it very useful. So let's quickly look at some differences between supervised learning and reinforcement learning. So in supervised learning, we have direct supervision. We are told what is the right answer, what is the wrong answer. In reinforcement learning, we are not told what is the right answer, what is the wrong answer. We have to try out. We have to say, maybe I think this is the right answer. This is the right way to do it. And if it's really the right answer, you get a positive reward. If it's not the right answer, you get a negative reward. And you learn from your experience. The second difference is that in supervised learning, you have instantaneous feedback. You immediately know that this input corresponds to this label. In reinforcement learning, that's not the case. You may have delayed reward. Think again, when you started to learn to walk, initially you were always falling down. Maybe you tried many different things, but you would always fall down. You would always get negative reward. And this happened probably for months, over years. Maybe it took you 1 year to learn how to walk. And only after trying for 1 year, you got a positive reward at the end of 1 year. So for 1 year, really, you were only seeing negative reward. So, and the true positive reward that you get after 1 year, that was your objective. So you can see that there can be huge delay in these things. And in supervised learning, time doesn't matter. In reinforcement learning, time really matters. It depends on what sequence of actions you take really matters what reward you get. And and in supervised learning, the data set is fixed. Agent does not affect the data set, but in reinforcement learning, the agent affects what subsequent data you see. Think of 2 babies. One baby started to maybe crawl. The second baby learned something else. It learned that maybe it can put its hands on the wall and then try to stand up. Now, the data that these 2 babies will see will be very different because they tried different exploration strategies. So what data you see, it depends on how you act. It's not fixed. It's unlike supervised learning. So I hope that clarifies what is supervised learning and what is reinforcement learning. Nonetheless, if you have any questions at this stage, feel free to ask. All right, I'll be taking more pauses every now and then, so you can ask questions if you have at that time. So now I guess I should continue for now. So let's look at some examples of recent breakthroughs in reinforcement learning. I said that reinforcement learning can be applied to many areas, but let's look at some examples. Atari games. Atari games, there is a set of games, a lot of games. And in the year 2016, there's a company called DeepMind. They used reinforcement learning, a single reinforcement learning algorithm called deep Q learning, to play multiple Atari games. So it was just one algorithm which they designed, and it was a reinforcement learning algorithm. And that single algorithm could play multiple games. And in many cases, it was doing better than humans. And in the year 2020, which is this year, they came up with an update on their algorithm, and they call it Agent 57. And this Agent 57 is a single RL algorithm that can play all 57 of Atari games and can outperform humans in all of them, which is amazing. It's a single algorithm that can play all the games. Here we have an example. This is an Atari game called Breakout, I guess. Yeah, Breakout. So the goal is to hit all the tiles, and this agent is trained with reinforcement learning. It tries something extremely clever. It sends the ball upwards and realizes that it doesn't have to do anything after that, which is a very clever trick it learned and using reinforcement learning. And in 2016 we had a very big news. There was a game between AlphaGo, which was an agent trained with reinforcement learning, and there was a match between AlphaGo and Lee Sedol. Lee Sedol at that time was the world champion in the game of Go. I heard that this was a national news in South Korea, so I believe all of you are aware of this. So in that year, AlphaGo defeated the world champion in the game of Go, and which is a huge news, because everyone at the time thought that we are years away from some sort of artificial intelligence that can defeat a human being or the world champion in such a difficult game like Go, which is extremely complicated. So this was a big achievement for reinforcement learning. And reinforcement learning can be applied for robotics. So here is an example. So if things are stacked up together and you want to pick them up, it might be hard because the gripper is too small to pick things up. So in this paper, or in this approach, the authors try to come up with a technique in which they can push things aside first, so that after that they can pick it up and throw it away. So, and this was trained with reinforcement learning. Okay, and this is a more recent update. It's from a company called OpenAI. They designed an RL algorithm that can solve the Rubik's Cube, but using a single hand. And it's extremely challenging because using a single hand, you have to turn all the sides of the cube, and it's extremely challenging. But they could do it using a single hand, and the technique they used is reinforcement learning. Yeah, so I believe that motivates you enough to appreciate how powerful this reinforcement learning algorithms are. So let's look at some terminologies that are used in reinforcement learning. So two important entities in reinforcement learning are the agent and the environment. So agent really is the brain, that it's the agent that acts that takes actions. So if you're trying to learn to walk, your brain would be your agent really. So here we have a brain which shows what the agent is, and we have an environment. So environment is basically anything that is outside the agent. Anything outside the agent is called the environment. So at every time step we take an action, and so agent takes an action that goes to the environment, and environment sends a reward and the next state, which makes sense. So you take an action and the environment will tell you how good your action was, and will also tell you what your next state is. And this happens again and again in a loop. So, and the next thing we are looking at is called Markov state. I forgot to mention, so state really here refers to what is your current state. So if you are in a world, maybe you can say, what is your XY coordinate? Where are you located? Anything that describes your current configuration is the state. So we have something called Markov state. A state is called Markov if the probability of transitioning to the next state given the current state is same as the probability of transitioning to the next state given all previous states. What it is trying to say is that given right now t, the time is equal to small t, and you know what is your current state is, that really has all the information that you would have if you had, say, all your past states. So what it is saying is that past states don't have any information, any extra information that is not there in your current state. And in reinforcement learning, we typically assume that our states are Markov. Now, let me show you an example why it might be a good idea to assume that states are Markov. Take, for example, this maze. You want an agent to solve this maze. So we have a start state and a goal state. And on the right-hand side, this is what we see at the current time state. So here we have a green circle, which is our agent over here. And let's say we know this is its current state, and we really don't know where it was in the past. Maybe it was here, or maybe it was here. It could have been here, or it could have been here. We really don't know. But logically, you would think that if your goal is here, you would now want to go down. It doesn't matter whether in the past you were over here or you were over here. Given you are over here at the current time state, you would want to go down. So there are, in many cases, it's the Markov assumption holds valid. If we have a good state definition, it's knowing the current state is sufficient information. You don't really care about storing past information. And the next thing is reward. Reward really is a scalar feedback signal. It indicates how well the agent is doing at time step t. So if it does good, it will get high reward or positive reward. If it's doing poor, it will get negative reward. And in reinforcement learning, the agent's job is to maximize the cumulative reward. It doesn't just care about the current reward. It cares about the reward it will get from current time step up into the future. Just like when you were a baby, you wanted to walk, you did the first day you tried to walk, you fell down, you got negative reward. The next second day you fell down, but after many days you got a positive reward. That's the positive reward you cared about when you started learning how to walk. Let's look at some examples of how rewards might look like. Say you have a helicopter, you want it to perform some stunts. What reward would you give the helicopter? If it does the desired thing, if it follows the right trajectory that you want it to follow, you give it positive reward. And if it crashes, which is a bad thing, the helicopter should not crash, you give it negative reward. If there's a game, if it positive reward for winning, negative for losing. If you are trying to invest money, you get positive reward for making more money, negative reward for losing money. So in many cases, it's really easy to define a reward structure that defines your problem. So if you are achieving what you want to achieve, it's positive reward, else it's negative reward. All right, and then comes the policy, which is extremely important in reinforcement learning. Policy is the agent's behavior. It's a mapping from state to action. So if you say, we usually denote the policy with pi. So here we have a deterministic policy, which means I'll give you the state S. I'll give the policy the state S. The policy will take that state S and tell what action you should take at this from this state. This is the example of deterministic policy. Sometimes we also have stochastic policy, which means it's a distribution over actions. So pi of A given S, it really says that what is the probability with which, I mean, it's a probability distribution over actions, and it weighs actions according to, like, as in ideally good actions should have high probability. And so it's a distribution. It says with what probability should I take action A given my current state. So for example, if you are driving a car, you could say that with 80% probability, I should go straight. If I'm in the middle of the road, with 10%, maybe I should go to the left. With 10%, maybe I should go to the right. And depending on the context, it's really a distribution. And uh, if I'm not wrong, in many problems, we usually assume a stochastic policy. And note that the final objective of RL is to obtain a good policy. So ultimately, this is the thing that you want out of your agent. You want it to have a good policy that can generate high reward. So finally, your objective, you should keep this in mind, that when you are training an RL agent, your ultimate goal is a policy. And next, we look at what is a value function. A value function says that what is the predicted future reward that you are going to get from your current state if you follow a policy pi. So mathematically, it is v pi of s is the expectation over pi, which really means it's an average, because you might get different rewards at in different episodes, but you take an average. You take your current reward, you take the next reward and the next reward, and so on. However, there is a discount factor, this gamma, which keeps getting multiplied. So the first reward is taken as it is. The next one is multiplied by gamma. The next one is multiplied by gamma square, and so on. And gamma is a discount factor. Gamma is always between 0 and 1. So what it is trying to say is that I care more about recent rewards, and I care less about future rewards. So for the first reward, I give it full weightage. The next reward, I weigh it down by a factor. Let's say gamma is 0.5, say, so it only cares half about it. And then when it goes to gamma square, it becomes 0.25, and so on. And if you take average of this is called a value function at that state S. So it says that if you are at this state S and you follow a policy pi, on an average, how much reward will you get in total? How much cumulative reward you will get? And this term RT plus 1 plus gamma times RT plus 2 plus gamma square times RT plus 3, this term is called the return, or sometimes it is called a discounted return because there's a discount factor. And when you take the average of this discounted return, it becomes the value function. So if you have a policy and you run that policy in the world once for one episode, say 100 time steps, and you calculate your return, you get this term, and you do it again and again, multiple times. You take the average, you get this value function. And then we have something called model. Model basically is a model of the environment. So the agent can think of how the environment operates. So model really says that if I'm at this state S and I take action A, what is the probability that I'll transition to the next state? And the model also stores information about the reward. So given that I'm at some state S and I take an action A, what is the probability that I'll get some particular reward? And you take an expectation and you store, which is an average, and then you store this reward. So just think of model as really a model of the environment. The agent will have in its mind how the world works. It may not be perfect, but it will have a model. Now, I understand there have been a lot of terms, so let's take an example to understand what each thing means, and we'll go through all the terms once again through this example. So here we have a maze, which we want our agent to solve. We have a start state and a goal state. And we want our agent to reach the goal as quick as possible. So what could be one reward function? The reward could be -1 per time step. And it makes sense because if your agent takes the shortest path, say it goes like this, it takes the shortest path, reaches the goal, it really has spent the least amount of time to reach the goal. So it will get the least number of negative ones. However, if the agent wanders around, takes a long path, it will get more negative return, because once the agent reaches the goal, the episode is over. So by episode, I mean really an episode. It starts and reaches the goal. So from start to goal, we have an episode, and at every time step, we give it the -1 negative reward. If it goes quickly to the goal, it will get low negative reward. And if it takes more time, it will get high negative reward. So really, to maximize the reward, it should go quickly to the goal. And so that explains what this is one valid reward structure. You could come up with a different reward structure based on what your objective is, and it's really your wish what problem you want to define. And in this case, what are the actions? So if an agent is in a given state, it can go to north, east, west, or south. It has 4 possible directions. And what is the state? The state is really the location of the agent. Wherever it is located, that is the state. So I guess reward, action, and state is clear. Next, we look at the policy. So here we are showing a deterministic policy, which means I give it an action, give it a state, it will say what is the right action to take. And these arrows show what is a good policy. So if I'm at the start state, I'll go left, I'll go up, I'll go right, I'll go down, and then finally I'll reach the goal. So this is one policy that we can use in this environment. And the policy really has a definition for all states. So even if you don't start, you don't start here, you don't need to reach here, your policy still says that, say somehow you reach here, you need to take this policy and reach the goal. Yeah, and then we look at the value function. So as I said, value function is on an average, how much reward will you get from your current state if you follow policy pi. And let's, for simplicity, assume that gamma is equal to 1. So I'll pull up the equation of value function again. So in this one, if you assume gamma is equal to 1, your value function is really the sum of all the rewards that you get in the future. So if you are in if you are at time t, from then onwards, what is the total reward that you get? You sum it up, and that would be your value function. So let's see what the value function in this case would be. If you are in this state, you can take right and you reach your goal in 1 time step, so it's -1. Remember our reward was -1 per time step. Let's say you are here, you need to take 1, 2, and 3 steps to reach your goal. So your value function will be -3. And likewise, you can fill up the value function in this whole maze. And it makes sense. So if you are in the starting state, on an average, it will take you it will take you 16 steps, and your reward is really -16. And this is the best you can do. If you would wander around, if you would go down and then come up, it can only be more negative because it will take more time steps. So for this problem, this is the optimum value function. This is the optimum policy. And and the model in this case, the model can be either the agent has the perfect model. It knows that if it takes east, it goes to the right. If it takes north, it goes up. Either that can be the case. Sometimes the agent may not have a perfect model. It may have wrong beliefs. It may think that if I take north, I go to the right, which is also possible. So again, agent can have a model which may be correct, which may be incorrect. And the model says what is the probability of transitioning from some state S to the next state S dash given an action A. So from S, you can go to multiple states. What is the probability of going to S dash given I take the action A? That is the model. Again, let's do a quick revision of all the terms. So we have an agent that acts in an environment. The environment is really everything outside the agent. You should remember that. The state is denoted by S. We usually assume that it's Markov. Actions, what actions can the agent take? Sometimes we use A to denote it, sometimes we use U. Rewards are denoted by R, and we have a policy, pi of A given S. And remember that this is what we finally care about. I mean, you don't care about what is the value function, you care about a policy that can actually act in the environment. And then nonetheless, we have a value function which is denoted by V of S. We have a model of the environment. And then 2 new definitions. Action space, it really says that what are the all possible actions that the agent can take. In our maze, the all possible actions were north, east, west, and south. The action space had 4 components. Sometimes it can be bigger. An observation space it says that the set of all possible observations that an agent can observe. For today's talk, let's keep it simple and assume that observation and state are equivalent. They really need not be the same, but for today's talk, let's assume that observation is same as state. So observation space in our case would be what are all the states that the agent can be in. And so ultimately this problem is formulated as a Markov decision process. It's called MDP, Markov decision process, where S is the set of states, A is the set of actions, P is the transition probability or the model, R is the reward structure, and gamma is the discount factor. And usually in reinforcement learning, we model the problem first as a Markov decision process, and we start from there on. There have been a lot of terms. If you have any questions, please feel free to ask right now. Or if you would want me to go over any topic once again, if you want me to repeat any part, that's also fine.
So far so good, and yeah, you can continue.
I'm sorry.
Yeah, we don't have questions up to now.
Okay.
Yeah.
Okay, that's good.
Yeah, yes, that.
So I think I have a smart audience today, which is great. Okay, so let's talk about some problems that we usually have in reinforcement learning. We have a problem of exploration versus exploitation, which really means that reinforcement learning is like trial and error learning. So you have 2 options. If you have discovered some skill, you can continue to do it to get more reward, which is called exploitation, or you could explore something new, and that is called exploration. Take for example, if you find out that certain stock in the market is good to invest money in, one option is you could exploit that stock. You could keep investing more of your money in the same stock, make more money. Which is good for you, and it's called exploitation. However, you could also explore. You could explore new stocks that you don't know whether they are good or bad, but it might happen that the new stock that you find out is way better than your previous best stock. stock, or it may be worse. So it's a risk, but really that's the learning process. You have to explore to learn something new. You can't always just exploit. So you have to, but you also have to strike a balance between the two, because if you just keep exploring, you will not get good reward. But if you just keep exploiting, you will not improve your current policy. So in reinforcement learning, you have to strike a balance between whether you are exploring and or exploiting, and it really makes sense in the real world as well. And the second thing is about long-term rewards. So in supervised learning, we get the feedback immediately, but in reinforcement learning, feedback can be long run. Like I said, when you were a baby, you start learning to walk, you don't get a good reward until maybe a year, which is a long time, but still it's the objective that you are trying to optimize for. So and another example could be and then sometimes what happens is that you might have to sacrifice short-term reward to get long-term reward in the long run. For example, when you invest your money, you are sacrificing the currently, because you are investing your money, you don't get to spend it now, but in the long run you make more money. So it's about the long-term return, the overall reward that you get, that you are trying to optimize for. And there are many algorithms in reinforcement learning, and they are categorized in you based on various criteria. So the first criteria is if a reinforcement learning algorithm uses just a value function and no policy, it's called value-based reinforcement learning. If a reinforcement learning algorithm uses a policy but no value function, it's called a policy-based reinforcement learning. And if it uses both a policy and value function, it's called actor critic. Now, a question might arise that I said that in reinforcement learning, the thing that we care about is a policy. How can there be something called a value-based function which doesn't have a policy? It doesn't make sense, because finally we want a policy. We want the agent to act. What value-based functions do is basically they have a policy, but they don't have an explicit functional representation of the policy. It's implicit, like using the value function indirectly you can get the policy. So that's what value-based reinforcement learning does. So value-based, policy-based, and actor critic. I believe the most popular ones are actor critic algorithms. They combine both. The second criteria is model free versus model based. So let's say your goal is to throw a stone as far as you can, and you are an RL agent. So, and you are model free. So if you are model free, you don't know how the world works. You just throw stones here and there and see what works best for you. That is model free. But if you are a model based reinforcement learning algorithm, you would know how gravity works. You would know that maybe if I throw at 45-degree angle, I will have the maximum distance that the stone can travel, because you understand how gravity works in your environment. You understand how all the physics works. So you are a model-based reinforcement learning algorithm. So usually having a model is helpful, but you don't always have access to a model. So these are two criteria again. These are two types again, using whether it's model free or model based. And then the third criteria is off policy versus on policy. So let's look at just on policy first. So on policy says that you can only use your current policy to collect data for training. Imagine learning only from your own recent experiences. Say you are trying to learn how to drive a car, and you use reinforcement learning to do it. Sorry. So in this case, let's say you just care about your experiences today, and you learn based only on those experiences to train your mind, your brain. That is on policy. On the other hand, off policy says that you can use data from a different policy to improve current policy. So there's a different policy, you collect data from a different policy and improve your your own policy. Imagine that you don't just learn from your experiences today, you also learn from your experiences in the past. Say what you did yesterday, you remember that if you made some mistake yesterday, you hit a wall, you try not to repeat your mistakes. So that makes sense. And another thing could be you learn from someone else's experience. Maybe you saw your friend drive a car, you learn from maybe one of your friends did well, another did worse. So you try to learn from their experiences. So that's off policy. You don't just learn from your policy, you learn from others people's policies. And the first thing is on policy, in which you just collect data from your own policy. So based on these criteria, there are many, really many RL algorithms, but we are just going to look at this shaded region, these I guess 45-degree lines, we are just going to work on these, on this area, which is, we are just going to look at model free methods, and we are going to look at policy based algorithms and actor critical algorithms. So in policy based, we will look at an algorithm which is called vanilla policy gradient, or it's also called reinforce. It sounds like reinforcement learning. Yeah. And the second thing that we are going to look at is actor critic. In actor critic, we are going to look at two kinds of algorithms. One is called advantage actor critic, A2C, and the second thing is called proximal policy optimization, PPO. You will, if you talk with someone who works on reinforcement learning, typically if they have a new problem, many a times people start with PPO because it works well in many environments. So it's a good algorithm, and this is what we used in our paper. So our final objective will be to understand what is PPO. Uh, so let's first start with understanding what policy gradient algorithms are. So okay, bear with me. We will have some math in the upcoming slides. So policy gradient is model free. We don't have a model. It's on policy. We just learn from our own experiences, and it's policy based because there's just policy and there's no value function in our RL algorithm. So let tau denote the state action sequences. So you start at state S0, take action U0, and you have a total of H time steps. So S0, U0, S1, A1 up to SH, UH, and we denote R of tau as to be to be the sum of the cumulative reward. So R of tau is the reward that you get at all time steps, and you sum over them. This is really the total reward, or it's what we call the return, right? And U theta is your objective, which you want to optimize. So remember, in supervised learning, we defined an objective to gradient updates. We are going to try to do something similar in policy gradient. So E here says really an expectation. So we are taking an average, and this is the sum of all the rewards that you get uh, given you follow your policy. So it can also be written as sum over all possible trajectories, probability of that trajectory multiplied by the return of that trajectory. So, and so this is really you can think of this as the average return that you get following your policy, right? Because you are summing over all possible trajectories, summing over all possible state action sequences that you can take. You are multiplying it with their probability, and then you are multiplying that with the return. So this is the return term, probability is the weight, and this is a weighted average. So ultimately it's an average of this return term. So higher this is better for your algorithm because we want to optimize the total return. So in our notation, our goal is to find theta. So we want to maximize over theta. So theta is basically the parameter of your policy. So your policy will have some parameters. You want to maximize over those parameters. These days, many people represent a policy as a neural network. So theta is in that case, the parameters of the neural network. You want to find the particular theta that will maximize this objective. So like in supervised learning, we talked about gradient descent. Here we will try to come up with what is the gradient of this objective, because if we have this gradient, we can use a similar kind of approach as we did with supervised learning in the gradient descent algorithm. So this is our objective, U theta. If you take the gradient with respect to theta, you have the gradient over here. Again, I will quickly walk through the math, but it's all right if you find it confusing. It's okay. I'll tell the final formula at the end. So, and the final formula is really what you finally need to know, but still I'll go through the math quickly. So you take gradient with respect to theta and sum over all trajectories, probability of the trajectory and return of the trajectory. As we know, gradient is a linear function, so you can move it inside. And then the gradient goes inside, and then you can multiply and divide by this p of probability of the trajectory. So it is fine because this will cancel out and we still get the same thing. And then what you can do is you can move this p of tau over here on the right. So from here to here, it's the same thing. I've just moved this p of tau from the left to the right. Now, if you remember basic calculus, gradient of logarithm is same as gradient divided by the term. So this thing is equivalent to the gradient of logarithm of the probability. So now finally we started with this term, which was probability multiplied by return. Here again we end up with probability, but instead of return we end up with an additional term over here. So this is, so what this term says is that it is the average, because probabilities are weights, so it's taking an average and we're taking the summation, so it's an average where the weights are probabilities just as before, but instead of the return we have this new term, gradient of log of probability of the trajectory and multiplied by the return. So we can, in practice, we can approximate this with, instead of taking the true average, we can take an empirical average, experimental average really. We can roll out m episodes, you can run your algorithm m times, you take the average of, you take the sum of this term over here, and I pull it up here. You compute this term for m times and then take the empirical average. And this really is the policy gradient algorithm. And again, here I have written it down with bigger text. So it's the average of gradient multiplied by the return. And then this is interesting because it says that I can take gradient of the objective even if my reward is discontinuous, because the gradient term is only coming with the probability of trajectory. It doesn't care whether the reward is continuous or discontinuous. So you might think it's strange that even if I have discontinuous reward, I can still take a gradient of this objective. Yeah, and let's understand what this policy gradient algorithm is saying intuitively. Now, if you remember the gradient descent algorithm, in gradient descent, we had this gradient uh, of the objective, uh, whereas in this case, we have a gradient term weighted by a return term. So let's understand what is going on. Let us assume that we rolled out 3 trajectories, which are shown in here, and say the first one gave you the highest reward, second one gave you slightly lower reward, and the third one gave you like really bad reward. So you don't want to take the third trajectory again. So what it is trying to say is that so the first trajectory will give you high positive return, second will give you something close to 0, and the third will give you high negative return. So you have 3 kinds of terms, and what it will finally do is, it is the gradient of the probability multiplied by the return. So let's see what it will do for the first trajectory. For the first trajectory, this return is positive, and this gradient will try to increase the probability of that trajectory, because inside we have log p of tau. So if you increase log p of tau, you are increasing p of tau. So you are taking gradient of this log p of tau, and you are increasing it because it's getting multiplied with a return which is positive. Let's look at the third trajectory. In this case, this will try to decrease the probability of the trajectory because it is getting multiplied with a negative term. So intuitively, you can understand that when you learn something, you do something, you realize that what you did was not good, you try to decrease the probability of taking that in the future. And if you did something good, you try to increase the probability of doing the same thing again. So this policy gradient really makes sense intuitively. You try to increase the probability of those trajectories which gave you high return, and you decrease the probability of those trajectories that give you low return, because that for low return the gradient will be multiplied with a negative term, and the gradient direction will be reverse, the direction in which you move your theta. And yeah, and after some mathematics, some calculations, you can also show that the policy gradient can be expressed in this way, which is you are taking expectation average over your policy. You take the gradient of the log of your policy uh, for taking action A given state T. So earlier I was taking this log over probability of the whole trajectory. It's a similar term, but now I'm doing it for every state. And you can show that these are really mathematically equivalent. So you have this gradient term multiplied by the sum of the rewards, which is the return. Yeah, so the reinforced algorithm is extremely simple. So you repeat until convergence. You sample some trajectories. You have your current policy. You roll out. You do whatever you want to do in the environment based on your current policy, and then you update your parameters in this way. So you have your theta. You do plus alpha, which is learning rate, plus expectation of your policy gradient. And this expectation in practice is approximated with empirical average. this is really like gradient descent, but here we have gradient ascent, because in supervised learning, typically we try to minimize the loss. Here we are trying to maximize our return. So we are doing plus over here. In supervised learning, we typically have a negative over here. This is an elegant algorithm because it's extremely simple, but it usually does not work. It does not work because there is high variance estimate of gradient, which means that if you compute this term empirically with experimentally, it will give you very different returns for every different run. So it is very unstable. This training is extremely unstable. So the reward increases, decreases. It's really unstable. It's hard to train. And the second problem is it's an on-policy algorithm. So let's say you sample some trajectories using, let's say you do 10 or 100 trajectories, and then you average over those in this. So after, so for those set of trajectories, you can perform only a single gradient update, which is a huge loss. Just think about it. You roll out your trajectory for several minutes, several hours, and then you can perform one gradient update. We know that one gradient update does not do much improvement. It does a small improvement. So this is extremely slow because it's an all policy algorithm, and you can relate it with the real world. Like if you just learn from your current experiences, you will learn extremely slow. But if you learn from other people's experiences, it will it will speed up your learning. You look at other people, how they're learning, and try to improve from their experiences as well. To speed things up. So people have applied a few tricks to improve this algorithm. First thing is called reducing variance, and this algorithm is called advantage actor critic. So we add an additional term over here. We subtract the v pi of st over here. So earlier we just had this summation. We now subtract the v pi. So and this whole term is called the advantage, and we write it as AT. So earlier we had expectation gradient of log of policy sum over sum of the rewards. Now we subtract the sum of rewards, subtract from it the value function at that state t. Now it kind of makes sense if you think about it. What is this term doing? It is saying that this is the return that you get, and we know that v pi is the average return that you would get. So how much is this trajectory better than the average? This is what this advantage term is saying. This is what you would anyway get on average, and this is what you are getting. Are you better than average or worse than average? And based on that, you update your parameters now. Instead of just using the direct return, you compare it with, you subtract the average. Yes, for those people who are familiar with reinforcement and machine learning and deep learning, you would know that in supervised learning, we typically normalize our data set. We subtract the mean and divide it by the variance and things like that, and that helps improve learning. You can think of it, the same thing happens over here. The second thing is called importance sampling. So earlier our objective was uh, it was pi theta multiplied by return, or maybe let me pull it up again. It was this, say, probability of the trajectory multiplied by return of the trajectory. Now we change it a bit. Probability of trajectory multiplied by return of trajectory is equivalent to policy multiplied by advantage. They're kind of equivalent. Only thing is now we are adding now we are really adding this ratio, this pi theta divided by pi theta old. So so earlier, I'll say it again. Earlier we did not have this term. We just had expectation over t, advantage. So just imagine that you want to improve your advantage, you want to improve your return really. But now we have an additional ratio, which is pi theta divided by pi theta old. What this helps you do is that now it can be mathematically proven that now you can use the experience of a different policy, which is theta old, to update your current policy, which is pi theta. This is useful because now, as we saw in the reinforced algorithm, after collecting samples, we can perform a single update. If you instead use importance sampling, you can do multiple updates. So learning can be made faster. So we looked at two things, the two problems: variance in the estimate, and that this is an on-policy algorithm. So advantage actor critic subtracts this value function, uses an advantage instead of the return, and this reduces the variance. And if you use importance sampling, you can also use your old experiences. So And then we come to the next algorithm, which is proximal policy optimization. Um, I won't go to the details of it, but it uses all the previous things. It uses policy gradients, it uses advantage function, it uses importance sampling. On top of it, it does something called clip. So this is the objective of it. It does, so you can see that some terms are similar. We have an advantage over here, and then we have this R term. R is really a ratio of pi versus pi old. I guess it's not so important to go into the detail, and we don't have so much of time, but the idea behind using this clipping thing is that you do not want to, first, you do not want to deviate too much from the old policy. So when you are doing multiple updates from your samples, you don't want to do too many updates and go too far away. And the second thing is you don't want to be over optimistic about what you can get in the future. So these are the things that it tries to prevent. And this is the PPO algorithm. Um, and we use this algorithm in our paper, and it really works well in many scenarios. I guess there has been a lot of math, but I hope you got the overall idea of what policy gradient algorithm does and what is advantage actor predict. And if you have any questions, please feel free to ask now.
And questions? A question? Uh, Mr. Deka,
Yes.
Mr. Deka?
Yeah.
Would you explain the advantage of model-based approach over model-free approach?
All right. Sure. So if you have a model of your environment, you don't really have to act in the environment to find something out. So if you have a model that says that if I go right, I will, maybe I'll pull up an example of the maze. See, in this case, there can be two approaches. One is you don't have a model. You try, if you don't have a model, the only thing you can do is you take random actions, and sometimes by trial and error, sometimes you'll get lucky and you will improve your policy. Instead, if you have a model, you don't even have to act in the environment. In your mind, you can think that maybe if I go there, I will reach the goal, and you can, improve your policy much faster. Does it make sense? Like, let's take, for example, when we were looking at the policy gradient algorithm, the policy gradient algorithm is really completely model free. There's no model. We don't know what the model is. By model, I mean, I don't know the transition probability. If I take an action A, I have no idea to what state I am going to go next. Really have no idea, but still I can improve my policy using this objective. But instead, if you would say me that also take this model and use this model to improve your policy, I could improve much faster, because then in my mind, I can imagine that I take this action and I go to this state. So maybe I should act in these ways and not in some other ways. Does it make sense?
Yeah. And this slide, on policy algorithm can perform a single gradient update even with so many samples.
Right.
Would you elaborate on that, why
sure.
it is so?
Yeah, it is so because you have this outer loop in which you repeat until convergence. So at every step you collect some samples and update the parameters. The important thing in this equation, if you see, this expectation is over pi, right? Pi is your current policy. If you update your policy, your pi becomes pi new. So if you take expectation over pi new, then this objective is not the same. So it's not mathematically valid. Does it make sense? Because you have to average over current policy.
Okay.
And if you the deriving importance sampling is not very hard. It's just you can think of, if you take this expectation over theta old, there will be a pi theta term over here. That pi theta old will cancel it by pi theta old, and this will really become pi theta with respect to new policy. So I mean, you can just imagine that this ratio is compensating for the difference between your old policy and new policy. This is the ratio that compensates it. Does it make sense?
Yeah.
If you use this, then you are free to use multiple updates.
Okay, thank you.
Yeah. Um, yeah, if you have any more questions, feel free. Else we can maybe take a short break at this point of time.
Yep. No more questions?
All right. Uh, are you guys back? Should I continue?
Yes, please.
Okay, perfect. So now let's talk about multi-agent reinforcement learning, which is uh, more relevant to our paper. So multi-agent systems can be beneficial in many scenarios. For example, disaster relief, defense against enemies or games. So if you are in a disaster scenario, you may require many robots to operate in an environment that can together, provide relief. So Okay, so types of multi-agent reinforcement learning. Multi-agent reinforcement learning is abbreviated as MARL. So there are two types, primarily cooperative and competitive. So in cooperative scenarios, many agents act in an environment for a common goal, and usually for success, it requires that the agents cooperate amongst themselves. For example, here a team of ants is trying to pick something up. A single agent would not be able to do it. They need to cooperate to achieve their goal. So in cooperative scenarios, can be seen in two ways. One is the centralized case. So let's say we have a whole team of n agents. You can treat the whole team as a single agent. How can you do it? You can say that the action of the team is the aggregation. You concatenate the actions of all n agents. I should have started from A1, but never mind. So a from A1 to AN, and the state is really S1 to SN. So if you take the states of all agents, put it together, they take the actions of all agents, put them together, you can treat this as a single agent reinforcement learning problem. And then you can apply all the techniques that we have in single agent reinforcement learning to this problem. So it's perfectly fine. But the problem is there is an exponential, the state grows exponentially, which means let's say and even the actions grow exponentially. If each agent can take k actions, then together there are a to the power k possibilities, which grows huge. So you can't really handle so many agents in a centralized manner. The other problem is when you have such huge numbers, you require huge computational requirements. And in many scenarios, it's not realistic to assume that uh, there is a centralized controller. For example, ants, they don't have a centralized controller. They act independently and they still cooperate. So centralized is not very, realistic if you think about it. And the other option in cooperative scenarios is a decentralized case. In this, each agent acts separately, but here comes a different problem. The environment becomes non-stationary. So remember I said that for an agent, from the perspective of one agent, everything outside it is the environment. So for agent 1, agent 2 to n is a part of the environment. And since everyone is learning, so the environment is changing. So because how the agent 2, 3 and 4 behave will change over time, and so the environment from the perspective of agent 1 is changing, and this makes training unstable. So that's the problem with decentralized case. And so people typically have a mix of it. So what they do is they use centralized training with decentralized execution. So which means at training time, they treat it as a centralized system, but at test time, each agent acts independently. So it might make sense because at training time, you may have access to a powerful computer. You can take care of huge computations, but at test time, they can act independently. Then comes competitive scenarios, in which one agent competes with another. So in cooperative, they have a common objective. In competitive, the objective is just the opposite. If agent one wins, the agent two loses, and so on. So and vice versa. So that was about competitive scenarios. Now I guess we have enough background to talk about our paper, which is natural emergence of heterogeneous strategies in artificially intelligent competitive teams. Now, let me first explain to you what the problem we are trying to solve is. So first, we have an environment which we call Fort Attack, and it's a mixed cooperative competitive environment. There's competition as well as cooperation. So there are in this environment, we have a fort over here, we have some guards, and we have some attackers. So it's kind of a game. The attackers try to come near the fort's door, and even if one attacker reaches, the team wins, which means of these attackers, even if one reaches here, the whole team wins and all the guards lose. And guards so naturally guards try to keep them away from this fort, and all agents can shoot lasers. Here we can see that some guards are shooting lasers, and if the laser hits any opponent, the opponent dies. So now our objective is we want to come up with some good guard strategies. How can we come up with good guard strategies in such a scenario? So there are a few challenges. first challenge is that it's a mixed cooperative competitive environment which is extremely complicated. There are so many agents. Sometimes you have to cooperate, sometimes you have to compete, and sorry, so it becomes difficult to model behavior of an agent by hand. You can't really, it's not trivial to write a controller by hand that can operate in such an environment. So in this case, it's natural to think that maybe reinforcement learning is useful in this scenario. We can define a reward function and try to optimize it. So challenge one is really not very hard for us now that we know about reinforcement learning. Challenge two is the chicken and egg problem. So let's say you want you want to train strong guard strategies. You first need strong opponents. You need competitive attackers. Now, again, hand coding strategies for opponents is also a difficult problem. So it's a chicken and egg problem basically. You don't have good guards, you don't have good attackers. How do you proceed from here on? The third problem is that modeling a large and variable number of agents. Firstly, as you can see, already we have 10 agents over here, which is a large number of agents. How do we model all of them? And the second problem is neural networks typically expect a fixed size input. So the neural networks that we use to model our policies, they would expect a fixed size input. Let's say at test time, one of the agents dies. So the size of the input would reduce for other agents. And that can't be handled by usual neural networks. They can't handle either decrease or increase, none of them. They want the same size of input that they saw during the training. So that's so how do we handle this problem? So these are the challenges. So if you have any questions at this point, I'd like to take them, else I'll proceed. Okay, I guess I'll proceed. So here comes an interesting topic, which is called graph neural networks. So which is abbreviated as GNNs. So neural networks used on graph structure. It's really, you merge graphs with neural networks. So imagine each agent is a node in a graph. So each node represents an agent, and there will be interactions with opponents, there will be interactions with teammates, and these interactions can be represented as edges, and there can be messages that can be passed along these edges. So naturally, it seems that in multi-agent scenarios, graph neural networks makes a lot of sense. You can represent the whole thing as a graph. Uh, let's see how the graph neural network thing works. But before going there, we will look at some definitions. So I will describe our method from the perspective of the guard team, so which we also call friendly agents. So let's say we are on the side of the guards. The other team has a symmetric representation, and xi represents the state of ith friendly agent, and it is the position, orientation, and velocity. So in the state, we have the position of the agent, the orientation, as well as the velocity. X opponent of J represents the state of Jth opponent in the other team. And S denotes the set of all friendly agents, all guards. S opponent denotes the set of all attackers. So these are basic definition. So in the upcoming slides, I will describe how agent 1 processes the observations of its opponents and how it interacts with its teammates. So here we have agent 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10. I will show you our approach from the perspective of agent 1, but all other agents do a similar symmetric thing. So it really makes sense just to look at one agent. And also here is our reward structure of our environment. So the important part, so the reward is a summation of many terms. The important two things are at the bottom. If all attackers are killed, then guards get high positive reward and attackers get high negative reward. And if attacker reaches the 4, then attackers get high positive reward and guards get negative reward. These are the important terms. Apart from it, there are some other terms which helps speed up the learning. So you have things like if you shoot an opponent, you get a small positive reward. If you die, you get a negative reward, things like that. But so the first 1 to 7 terms are really to speed up learning. The actual objectives are in 8 and 9. And if you try out reinforcement learning, many a times it takes a lot of time to train. So we have to come up with such reward structures to speed things up. And yeah, so let's understand how agent 1 interacts with its opponents first. So first of all, we have something called, we try to form embeddings, or you can call them as messages. So H1 is defined as F theta A of X1. So X1 is the state of agent 1. State is position, velocity, and orientation. you pass it through a function f theta of a and get h1. In our case, f theta of a is a neural network, and wherever you see f theta of a, f theta of b, whatever, what I'm referring to is really a neural network, and the theta represents the parameters of that particular neural network. And you now start to understand why it's called graph neural networks, because we have a graph and we are using these functions, and we are using neural networks over these functions, so it becomes a graph. It becomes graph neural networks. And so h1 is f theta of a given x1. So it takes x as input and finds an embedding. Similarly, it does a similar thing with all the opponents. So in this graph, I'm showing that opponent states are, let's say we have 3 opponents, so they have 3 different states. You pass them with through the f theta b function, you get their embeddings. These are called embeddings. Embeddings are vectors basically. And one important thing to note is parameters are shared across this within the same team. So f theta a of agent 1 is same as f theta a of agent 2, but it's not the same between opposing teams. So the attackers and guards will have different parameters, but within the same team they share the parameters. All right, now next we compute what is called an attention. So I have this h1, I'll say this again, h1. From this equation I have an embedding of agent 1, and I have embeddings of all the opponents, and then I do dot product pairwise of the agent one's embedding with the other opponent's embeddings. So this is what I represent over here. I do a dot product, and then this dot product gives me phi hat 1 of j, and then I normalize it using this formula. So phi hat 1 of j will basically be phi hat 1 of say 6, phi hat 1 of 7, etc. So you will have many such terms. You normalize them so that this phi 1j, this term sums over 1, and this is called the attention. So phi 1j says how much attention agent 1 pays to opponent j. So agent 1 has opponent, this opponent, this opponent, and this opponent. It will pay different amounts of attention to each one, and how I'm computing this attention is basically by taking a dot product between these vectors pairwise. Now once I have the attention values phi ij, phi 1j, I use that as a weighing factor. So I sum over all the opponents. I take the attention value and the opponent's embeddings. So it's very intuitive. I have opponent's embeddings. I do dot product. I compute the attention, and then using this attention, I take average of these embeddings. And I get E1. So essentially, if you think about it, this E1 has information about all the opponents in a fixed size vector. This is good because even it doesn't matter if you have 3 agents or 30 agents, the size of this embedding is fixed. So we are able to deal with a variable number of agents. And once we, okay, and some important things to note, uh, when I say that opponents, we compute these opponent states and do dot product, the opponents really are not sharing their information with the guards, because why would opponents share their information? They are in the opposing team. How does agent 1 then get these x opponents, x opp values? It makes its own observation of the opponents, because agent 1 is free to observe its opponents. That's how it gets these x opps. These are not shared by the opponents. And the second thing is phi ij summation over j is equal to 1. So the attention value that agent 1 gives to different agents is different, but they always sum to 1. So this ensures that the total attention that agent 1 is paying to opponents is fixed. And finally, we concatenate agent 1's own embedding with the opponent embedding and get the final agent embedding, which is denoted by capital H. So this capital H has information about the agent 1 itself as well as all the opponents in a fixed size vector. Now, similarly, it does the same thing with its teammates, but using different neural network parameters. Again, it computes an embedding, which is the embedding we get from this stage. We already have this. We do this for all the agents, and then we take a dot product and finally pass it through a nonlinear function, which is again a neural network, and then get the final embedding. So this computation is just like the previous computation, just this time it's looking at its own teammates. So this is the first attention layer that we have, in which we look at the opponents. After we look at the opponents, we look at our own teammates, and finally we have this H, capital H, which capital H, which will contain the information about all agents in the environment, including itself, its teammates, and its opponents. And this is a fixed size vector. It doesn't matter how many opponents or how many teammates it has. The size of this vector is same, which is very useful for us. And finally, this is how we define our policy. So policy is nothing but we pass our final embedding with a final nonlinear function, another neural network, and take a sigmoid, which sigmoid gives a probability distribution. So, and this is what our final policy looks like. So really the graph neural network helped us compress all the information into a fixed size vector on which we use a finite neural network to express what our policy is. And again, I'll say that this is called graph neural networks because it's really a graph data, and uh, it's neural networks because we have many f theta terms. We had f theta a, f theta b, and we had f theta c and f theta d. So we had multiple neural networks and we have a graph architecture, so it's called graph neural networks. Once we have a policy that we have modeled, uh, training it is extremely simple because we can train it using proximal policy optimization. And we trained our algorithm on a commodity laptop with a GTX 1060 GPU. It's kind of old GPU right now, but still it worked for us. And training takes about 2 days without parallelizing the environment. So we left it to train for 2 days. Um, let's quickly talk about what are the advantages of using graph neural networks with attention. First is scalability. We can scale to a large number of agents because the number of learnable parameters is fixed. They are theta a, theta b, theta n, theta c, and theta d. It does not depend on the number of agents. So even if you have a lot of agents, you can still deal with that. The second thing is variability. Because we are passing through an attention layer in a graph neural network, it doesn't matter if I have 3 agents or 10 agents or whatever, I can deal with that. Yeah, and finally we had one more problem, the chicken and egg problem. How do we don't have good attacker policies to train against. So even if we have a graph neural network architecture with PPO, how do we train it? What do we train it against? So we train both teams together with reinforcement learning to solve this problem. So both teams don't know what to do, but we train both of them together. So each team improves over time. And this provides incentive for the other team to improve. And we will see this in detail later as well. So that's fine. And so the algorithm looks pretty simple. It's like at every training iteration, we update the guards with one step of PPO, and we then update the attack, and we also update the attackers with one step of PPO, and then we repeat this for many iterations. Let's quickly summarize our method. So uh, the challenges that we faced are here, and the solutions are on the right hand side. So first challenge was hard to model by hand. Solution is pretty simple, use reinforcement learning. Second thing was large and variable number of agents, so use graph neural networks. Chicken and egg problem, train them together. So this table summarizes our method. If you have any questions so far, feel free to ask.
Mr. Deka?
Yeah.
Yeah, I have a question that the agents in a friendly team can communicate or exchange information with each other?
So at training time, yes. At testing time, we are assuming no. So at training time, they are sharing the parameters. So that is how they are kind of exchanging information. And yeah, does it make sense?
In execution time?
In execution time, we assume that they are not really sharing any information. So each agent can observe the opponent and in its own teammates, right? So that's how it computes this computations on the graph neural network. I would like to clarify one point. So in this line, I say that messages are passed along the edges. We call them messages, but they are not really messages. So say, for example, this yellow agent needs something from its teammate shown in green. It won't really ask something from it. It will observe what its state is and uh, compute, uh, compute the vectors itself. It's not really sharing it. Does it make sense?
Mm-hmm. Okay, thank you.
Yeah. Yeah. Okay, so after a lot of maths, finally we have arrived to the interesting part. I hope you like this part. I believe it's extremely interesting. So when we train our agents together, we observe an evolution of strategies.
Mr. Deka,
So yeah,
we have one more question.
I
sure.
have question about the graph neural network. I cannot
Okay.
understand how did edges information are composed. How did you make
How
the adjacency matrix?
what
For,
is the adjacency matrix?
yeah,
Oh, in this
I
case,
mean,
I
how did you
assume.
compose the adjacency matrix for the graph neural network?
All right. Okay. So in this case, I assume that the each agent is connected to every other agent. So I assume it's a fully connected graph. So every node is connected to every other node. So it can so it's a full adjacency matrix basically. But in practice, you could do something else. You could maybe consider only the other agents which are within a radius of yourself.
So you
You
mean
could do
the
that and try
all
to.
agents are connected, all the attackers and the
Right. Yeah.
guards?
For this example, yes. I mean, in my implementation, yes, but you could use only the neighboring agents if you wish.
Okay, thank you.
Okay.
Let's continue.
Okay. Sure. Yeah. I believe the final part would be interesting, and there's no more maths. The maths is all over. Um, so here I'm showing the reward curve for the attackers and the guards. For attackers, I'm showing it in red, and for guards, I'm showing it in green. You can see that the rewards oscillate over time. It's an oscillating curve. It's not increasing or decreasing per se, it's oscillating. And these oscillations have some local minimas and maximas. And if you observe roughly approximately the reward curve for the attackers and the guards, they are mirror images really. And it makes sense because if the guards are losing, it means the attackers are winning and vice versa. So victory for one team means defeat for the other. And we can see that there are these maximas and minimas. Each maxima and minima corresponds to an increasingly complex strategy that the agents develop in response to the previous strategy of the opponent team. So, so in particular, we observe 6 different strategies, and let's go through them one by one. So when we start training, we see that the agents randomly move around. They try to make sense of the Fort attack environment. They don't really know what to do. You can see they seem like stupid agents who are moving here and there, doing extremely random stuff. What they're doing does not make sense because they have just started learning. Okay, and after some time, what happens is that the attackers learn to move towards the fort, and the guards learn a simple strategy to defeat them. They just flash their lasers all the time. So any attacker that tries to approach dies. So it's a simple strategy on the guards part, pretty effective. The guards keep winning at this stage. So now it's challenging for the attackers. They have to come up with something smart. So what they do is they start sneaking in. So they move in different directions. Some of them get died, but one of them manages to sneak in from the side and reaches the goal. Now remember the objective of the attackers is that only one of the attackers needs to reach the fort. All of them don't need to reach the fort. So it's okay to sacrifice some of the attackers if if even one manages to reach the fort. So now it's getting more challenging for the guards. What do? They learn to spread out and kill all the attackers. So they prevent attackers from sneaking in. So they spread out and kill all the attackers. Now at this stage, it's extremely difficult for attackers. So they learn the strategy of deception. So what they do is, yeah. So what happens is most of the attackers start moving in from the right and one holds back on the left. And these which move from the right start shooting aggressively. This diverts the attention of the guards to these agents and they forget about this one agent which was left behind. This one agent sneaks in at the right moment and brings victory to the whole team. And again, this is also interesting because uh, we are sharing parameters across agents on the same team. So if we are doing so, then really they are homogeneous agents. But this behavior requires heterogeneous behavior. Some of them need to move to the right, one of them needs to stay back. So hence the title of our paper, Natural Emergence of Heterogeneous Strategies. Now let's look at one more interesting thing. Uh, so over here, I have a reference card. If you see carefully, there's a green dot at this card, which is numbered 1. So this is the reference card. All the other agents have yellow rings around them, and these rings represent the size. The size of the ring is proportional to the attention that agent 1 pays to each of these agents. So agent 1 pays different amounts of attention to all the agents, and it's represented by the yellow rings. Let's see what happens. So initially, agent 1 pays roughly equal and low attention to all the attackers because they are all far away. It does not care much about anyone in particular. But after some time, what happens is this one agent is shooting aggressively from the right. So agent 1 has started to pay high attention to this agent because it's shooting from the right hand side. um, and so all and similar it would be the case with other agents because they are also moving to the right, but they didn't realize that this was sneaking in this agent, and at the right moment this agent number 9 moved ahead, and at this stage agent 1 realizes that it's I should have really paid attention to this agent, but it's too late for it because now agent 9 has moved ahead and it reaches the goal. So this is the deception strategy that that the attackers learn, and this was the attention visualization. And finally what happens is finally guards spread smartly and they end up killing all the attackers, so and they win. And now these were the 6 strategies, and now if you think about it, we now have a set of attacker policies. We have 6 strategies. We can, if we want our guards to perform well against all of them, we can train a single guard policy against all the attacker policies. And the reward curve in this case is steadily increasing, which is expected because the attackers are not learning at this stage. We have their policies fixed, and we are training a single guard policy against them, and we are calling it ensemble strategies. So the key observations of our paper are that competition can lead to natural emergence of strategic behavior. Uh, Heterogeneous strategies can emerge out of homogeneous agents. So the agents were all homogeneous, but they learned heterogeneous strategies, which is extremely interesting. And remember, nowhere in the reward structure we encouraged it to learn such strategies. It came up with these strategies itself. It learned that if the team does this kind of heterogeneous strategy, it can deceive the guards really. And uh, the third thing is that graph neural networks can effectively model multiple agents in a mixed cooperative competitive environment. So if you like, you can play with our code base. Our code is available in this link. Um, uh, if you don't want to train, it's fine. I have provided trained models using a single line. You can visualize how the trained models operate. Basically, the videos I've shown. Here are some future directions. We saw that natural emergence of deception strategy required heterogeneous behavior amongst homogeneous agents, and it evolved by itself. If we want to explicitly encode such strategies, we can make a simple extension. We can have different sets of policy parameters within the same team. So some agents can, so they need not share the same parameters throughout the whole team. They can have different sets of parameters. This, for example, this might lead to that some guards are aggressive and other guards are defensive, things like that. We can explicitly encode it if we wanted to. Uh, we could also try out with more number of agents to see how scalable it really is. Um, and again, we did not compare against a hand-coded strategy. We said that it's hard to come up with such strategy, but maybe if we could, we could possibly compare it. And then another interesting direction is right now the guards don't think of how the attackers are thinking. A model-free algorithm. It's not a model-based algorithm. Instead, it could create a mental model of the opponents, which could lead to better performance. And this has been explored in different papers. Yeah, so do you have any questions?